Have you ever looked up at the night sky and wondered why planets move in orbits? Or how a ball thrown in the air knows how to come back down? The answer lies in the fascinating world of classical mechanics. It's like a secret code that unlocks the mysteries of motion in our universe. From the smallest atom to the largest galaxy, everything moves according to these elegant laws. Classical mechanics explains how objects move, why they move, and what happens when they collide. Join us as we embark on a journey to understand the fundamental laws that govern our physical world, making physics fun and easy to understand. Imagine a ball rolling on a perfectly smooth, endless floor. It would keep rolling forever at the same speed and in the same direction, right? That's Newton's first law in action. It states that an object at rest stays at rest, and an object in motion stays in motion with the same speed and in the same direction unless acted upon by an unbalanced force. This tendency to resist changes in motion is called inertia. It's the reason why you feel a jolt when a car suddenly brakes or accelerates. The ball wants to keep rolling and you, sitting in the car, want to keep moving at the same speed. Inertia is a fundamental property of matter, and it plays a crucial role in understanding the motion of objects all around us. Newton's second law tells us that the force acting on an object is equal to its mass times its acceleration. In simpler terms, the harder you push something, the faster it will accelerate. Think about pushing a shopping cart. A gentle push will give it a slow acceleration, while a strong push will make it accelerate much faster. The mass of the object also matters. A heavier shopping cart will require more force to accelerate at the same rate as a lighter one. This law is expressed mathematically as F equals sine ma, where F is force, m is mass, and a is acceleration. Newton's second law helps us understand how forces influence the motion of objects, from rockets launching into space to cars accelerating on a highway. Newton's third law states that for every action, there is an equal and opposite reaction. This means that whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first object. Imagine jumping on a trampoline. You push down on the trampoline, action, and the trampoline pushes back up on you with an equal force, reaction, propelling you into the air. This law is also why rockets work. The rocket expels hot gas out of its engines, action, and the gas exerts an equal and opposite force on the rocket, reaction, propelling it upward. Section 5. Momentum, the power of motion. Momentum is a measure of an object's motion. It depends on both the object's mass and velocity. A heavy object moving at a high speed has a lot of momentum, while a light object at rest has zero momentum. We can calculate momentum using the following equation. P equals mv, where P is momentum, m is mass, and v is velocity. Momentum is a vector quantity, meaning it has both magnitude and direction. The concept of momentum is crucial for understanding collisions and explosions. In a closed system, the total momentum before an interaction is always equal to the total momentum after the interaction, even if the individual momenta of the objects involved change. This is known as the law of conservation of momentum. Section 6. Collisions. When objects collide, momentum plays a key role. Collisions happen all around us, from billiard balls colliding on a pool table to cars crashing on a highway. In any collision, momentum is transferred from one object to another. The outcome of a collision depends on the masses and velocities of the objects involved, as well as the nature of the collision. In an elastic collision, like the collision of billiard balls, both momentum and kinetic energy are conserved. In an inelastic collision, like a car crash, kinetic energy is not conserved, and some of it is transformed into other forms of energy, such as heat and sound. Understanding collisions is essential for designing safer cars, analyzing the aftermath of accidents, and even studying the formation of planets. Section 7. Rotational dynamics, spinning objects and angular momentum. So far, we've focused on linear motion, which describes objects moving in a straight line. But many objects also rotate, like spinning tops, planets orbiting the sun, and even figure skaters spinning on ice. Rotational motion is governed by a set of principles analogous to those governing linear motion. Just as linear momentum describes the tendency of an object to resist changes in its linear motion, Angular momentum describes the tendency of a rotating object to resist changes in its rotational motion. Angular momentum depends on the object's moment of inertia, which is a measure of how its mass is distributed around its axis of rotation, and its angular velocity, which is the rate at which it spins. Section 8, From Spinning Tops to Orbiting Planets. Understanding Rotational Dynamics. The conservation of angular momentum plays a crucial role in understanding a wide range of phenomena, from the graceful spins of figure skaters to the stable orbits of planets around stars. For example, a figure skater can increase their spin speed by pulling their arms closer to their body. This decreases their moment of inertia, and since angular momentum is conserved, their angular velocity increases to compensate. Similarly, the Earth's orbit around the Sun is governed by the conservation of angular momentum. As Earth gets closer to the Sun in its elliptical orbit, its speed increases to conserve angular momentum. Section 9. Our Classical World, a symphony of motion governed by timeless laws. Classical mechanics provides a powerful framework for understanding the motion of objects in our universe. From the seemingly simple act of throwing a ball to the complex dance of planets orbiting a star, these timeless laws are constantly at play, shaping the world around us. Imagine a world without classical mechanics. We wouldn't be able to predict the trajectory of a projectile, understand the forces involved in a car crash, or even comprehend the orbits of celestial bodies. By unraveling the principles of motion, classical mechanics has not only deepened our understanding of the universe, but also paved the way for countless technological advancements. From the design of bridges and buildings, to the development of cars, airplanes, and spacecraft. As we continue to explore the vast expanse of the cosmos, and delve deeper into the microscopic world of atoms and subatomic particles, the elegance and power of classical mechanics continue to inspire awe and wonder, reminding us of the profound order that underlies the apparent chaos of the universe.